So thus far in class, we've been talking about planar mechanisms, which are a special form of spatial mechanisms. So now let's kind of take a step back and look at spatial mechanisms more generally. We'll talk about some ways that we can define the mobility of these, and then start to look a little bit more specifically at spherical mechanisms, which are, again, a specific type. So let's take a look at some examples of spatial mechanisms. So one of the most common ones that you might be familiar with is a universal joint or a hook joint that you see in the upper left there. Now, a hook joint is used to transmit rotation between two shafts which are intersecting but are not coaxial. So this allows rotation between those two shafts and allows transmission of that rotation. Now, this hook joint happens to be a special type of spherical joint, and the angle between the joints here is 90 degrees. And I've got really two different views of this same spherical mechanism. One is where we're looking at the traditional cross or the spider that you would see in a hook joint. But then this other one right here where we have a 90-degree angle between the two, those are kinematically equivalent and would create the same motion. Now another example of a spatial mechanism is a swatch plate mechanism where we have rotation of this red shaft right here, which causes this angled plate to rotate. As that angled plate rotates, it causes these pistons to reciprocate back and forth, and this is often used in a pump type of a mechanism or maybe a compressor. Another application is this bone cutter right here that happens to be another spherical mechanism, where as the surgeon would drive these handles here, it causes this motion of the end effectors and cutting of the bone. And because we have these four joints right here, they all intersect at one location. This happens to be another example of a spherical mechanism. So we'll look at a few more examples in class where I'll show you some actual hands-on pieces that you can take a look at. So now we've talked a little bit about what a spatial mechanism is. Now let's start to look at what defines them. And this really comes down to what the joint types are. Obviously, we can have links connecting all of these joints, but the joint types are a little bit different than what we've seen in the planar world. So let's talk about some of the options here. So one of the first that you're probably most familiar with is the revolute joint that you've seen already. And one thing that revolute, let's see if I can spell that correctly. One thing that we do with spatial mechanisms that we did not do so much with the planar mechanisms is that we give all of these joint types a letter. So the revolute joint will give an R. The next joint next to it is a prismatic joint, also referred to as a slider. And for the prismatic, we use a P. And then we can move on to this screw joint over here and realize that all three of these allow 1 degree of freedom. The revolute joint, we only allow rotation about one axis. Prismatic, we only allow sliding, and that's what that little triangular piece is telling us, is that we're not allowing rotation about that as well. And the screw joint, we have translation and rotation, but they are coupled through the lead angle that we have. And so, again, we have 1 degree of freedom with a screw joint, and the screw joint is typically S sub L as a screw joint, and L being the lead. Now, we can recognize that also a revolute and a prismatic, these are special forms of screws where we might have infinite or 0 degree screw angle or lead to that. All of those allow 1 degree of freedom. These next joints that I'll talk about allow more degrees of freedom, where on the bottom here I have a cylindrical joint, and we use a C for that, cylindrical. That's C. The next one over would be a spherical joint, and believe it or not, we give that a G. The reason that we give it a G is because it's also called a globular joint, so a spherical or a globular joint. And then the last one over on the right here is a planar joint. And this will give an F. You can also think about it as a flat joint, two flat pieces. So the cylindrical joint allows translation and rotation. The spherical joint allows 3 rotations, so we get rotation about the X, about the Y, and about the Z. So 3 rotations for the spherical. And the planar allows 2 translations and 1 rotation. So the spherical and the planar allow 3 degrees of freedom. The cylindrical allows 2 degrees of freedom. All right. So now that we've defined all of these different joint types, why do we need to pay attention to them? Well, the reason is that we name our spatial mechanisms based on what their joint types are. So this mechanism that you see here, we start at their input side and we move to the output side. If my input happens to be that revolute joint, this mechanism here would be referred to as an RGCP. So we'd have a revolute, globular, cylindrical, and prismatic joint. So that's how we would define this mechanism, going from the input to the output. If our prismatic joint happened to be the input, then it would be a PCGR. Now you can imagine that because we have so many different joint types, we can create an enormous number of different spatial mechanisms, and it can be overwhelming at times. There happens to be 435 at least single degree of freedom spatial mechanisms. So with all that said, Harrisburg, a famous kinematician, did a study here and looked at a whole list of 1 degree of freedom mechanisms and said, what does he determine as most useful of the 1 degree of freedom mechanisms out there? And here's a listing of them, and you can see that revolute, cylindrical, cylindrical, cylindrical is one. Moving on to the one that we had just done the example of. These are the ones that he determined were the most useful. And the one thing that I find quite interesting is just how the screw joints are used here, where the lead angles can be very shallow, such that this almost acts as a prismatic joint while creating some rotation at the same time. So not what we normally think of as a bolt with a nut on it for being that screw axis. So we can have a very, very long lead angle. All right, so we've got some useful 1 degree of freedom mechanisms. We can imagine we have lots of 2 and 3 and 4 degree of freedom mechanisms. So we define the mobility in a spatial mechanism using the Kutzbach criterion, which is very similar to what we had done in the planar world. And the way we start off with the mobility equation is just saying my mobility, m, and this is mobility, this is equal to 6 times the number of links that I have. So this is n is the number of links, minus 1. That's the start of the equation. So why 6? Well, anytime we place a link into the spatial world, we have x, y, and z, as well as rotation about x, y, and z, and therefore 6 degrees of freedom. N being the number of links, every time I add a link, I add 6 degrees of freedom, but we don't count ground because ground is stationary and has no mobility. So that's why n minus 1 times 6. Now we're going to subtract off the mobility that is removed by each one of the joint types. So how we start with this is I'm going to subtract off 5 degrees of freedom for every J1 joint. And a J1 joint is a joint that allows 1 degree of freedom. So that would be the revolute joint, the prismatic joint, the screw joint. And then I'm going to subtract off 4 times the number of J2 joints, so allowing 2 degrees of freedom like a cylindrical joint, minus 3 times J3, minus 4 times J4, minus 5 times J5. And obviously we could have 6 being J6, but that would be a joint that has no mobility, which really isn't a joint. So all these J's, these are the number of, let me just write it out for you. J sub I, this is equal to a joint with I degrees of freedom. So that's how we determine our mobility in a spatial world. So let's look at an example of this. Here happens to be a platform type of a mechanism where I have a ground plane that's down here, so that whole ground plane. And attached to that ground plane I have 3 revolute joints. So I have this one here, this one, and this one over here. So 3 revolute joints. On each one of the links coming up from those revolute joints, I have a prismatic joint or a slider joint that moves along that axis there, this axis, and this axis. Above all of those, I have globular joints or spherical joints that then connect up to this top moving platform. So let's apply Kutzbach criterion to this and determine how many degrees of freedom we have. So I start off by naming or numbering my joints. So I have 1 degree of freedom for the base plate, 1 link for the base plate, and then 2, 3 for the top of the prismatic, 4 for the top platform, 5, label this 6, 7, and finally 8. So I have 8 links in this mechanism. So let me just start off my equation. So this is 6 times 8 minus 1. And then I'm going to subtract off how many J1 joints I have. And these are the revolutes and the prismatics in this case. So I've got 3 revolutes around the bottom, 3 prismatics above those, so a total of 6. So I get 5 times 6. And then I'm going to subtract off any cylindrical joints, which I don't happen to have any, so I have no J2 joints. But I do have 3 J3 joints that happen to be my spherical joints. So I'll subtract off 3 times 3 joints. So when I put all this together, I get 42 minus 30 minus 9, or a total of 3 degrees of freedom. And I think that we can visualize these 3 degrees of freedom from this mechanism, that each one of these locations right here, so this location, that really can translate along the axis as well as rotate about the lower revolute, but it can't then move side to side, if you will. So that really has to stay in that one plane, and because of that, we can then imagine that at all 3 corners, and then imagine kind of the rotation of that top moving platform. So those would be the 3 degrees of freedom for that moving platform, or really the rotations that it can have about that plane that's fixed by the revolute in the planar or in the prismatic joint. All right, so that's how we apply the mobility equations. Let's take a look at what else we can leverage from what we learned in the planar world to the spatial mechanism world. So here's kind of some correlations that we can look at from planar theory out to spherical and out to spatial. So spatial is a more general form. Spherical is a little bit closer to a planar mechanism where instead of having all of our joints being, the axis of all of our joints being aligned or parallel, here we have them all intersecting at the center of a sphere. So a little bit of an extension, whereas spatial really gets out there. But let's take what we've learned from the planar world and talk about how it applies. So Gribler's equation, we just saw that we've got the Kutzbach criterion that applies to both spherical and spatial. We can have poles. Remember we had rotopoles that described rotations between precision positions. So we have a pole, we have a rotation axis in the spherical world, and a displacement screw in spatial. We have instant centers of velocity in the planar world, and similarly in the spherical and the spatial. We have image poles, and we can have similar image poles in the spherical and the spatial world. And same thing as we go into pole triangles and center point, circle point pairs, Burmester curves. We see all of those, as well as the Euler-Savery equation, which applies to curvature theory. All of these theories that we have used or really talked about in the planar world apply to spherical mechanisms and spatial mechanisms as well. So with that said, let me do a little bit deeper dive now into spherical mechanisms to help you visualize what these things look like, and we can then use that to start to build on that and do some synthesis of these spherical mechanisms. So here's a video of a spherical 4-bar mechanism, and you can see that we are moving through the range of motion with this, and I've got a crank as the green input link, and this happens to be a crank-crank mechanism. But the most interesting thing that I want you to recognize is that all of the joints intersect at the same center of the sphere, and therefore that's why we call this a spherical mechanism. So all the joints have to intersect at the center, and manufacturing these with precise tolerances such that it occurs is important to prevent binding of these mechanisms. We'll see in class in just a little bit that when we do a mobility analysis of a spherical mechanism, we might not find what we expect. So we represent our spherical mechanisms very similar to what we've done with our planar mechanisms, where instead of the link lengths that we have in planar world, now we have the link angles, or the central angles that they occupy. So the central angle of the crank link, we give that the angle alpha. The central angle of the output link is beta. We have gamma for the coupler, and we have zeta for the ground link. So you can see that regardless of what the diameter is or the radius is of my sphere, these central angles define the motion of a spherical mechanism, and that's how we represent them. So just like we had done with our planar world, we then can look at what do the coupler curves look like in a spatial in a spherical mechanism. And remember that these are now moving on the surface of that sphere. So it's a little bit difficult to visualize these in 3D space. So sometimes we then break these up and put them into an XY or a YZ coordinate space so we can visualize these from the top or the side, just because it's a little bit more difficult for us to visualize these on a sphere, if you will. But these coupler curves apply, and we're able to synthesize our mechanisms to create desired coupler curves. And remember that we can have that coupler point be anywhere on the coupler. So we can extend it out to different locations and therefore create different coupler curves. Now, just like we had done in the planar world when we had done precision position synthesis, we got to the point of doing 4 precision positions. Well, we could do the same thing with our spherical mechanisms and create the Burmester curves for the ground and the moving pivots. And this happens to be an example of a set of Burmester curves for a 4-bar mechanism where I happen to have picked, or the solution here has been picked for the ground pivots A0 and B0 and the moving pivots A1 and B1. And again, instead of using link lengths, we're using the central angles of each one of these links to define the mechanism. So hopefully from this video you can see that a lot of what we've learned in the planar world extends out to the spatial world, and the spherical mechanisms are kind of a nice stepping point as we go from planar all the way out to more complex spatial mechanisms. So we'll do some more development of the spherical mechanisms in class.